Okay, then welcome everyone to the weekly colloquium of the Physics Institute of the UNAM in Cuernavaca in Mexico. Our guest today is Pablo Rodriguez-Fernandez from the Massachusetts Institute of Technology, where he works as a research scientist in the Plasma Science and Fusion Center. Yeah, let me say some few words on his vitae. Pablo studied industrial engineering at the Polytechnic University of Madrid and holds a master degree in mechanical engineering from Drexel University. Despite his engineering background, Pablo focused on the study of transport phenomena with computational plasma physics for his doctoral degree, which he received in 2019 from MIT. In his work, he utilizes state-of-the-art machine learning techniques to solve complex physics and engineering optimization problems. Pablo has been leading the efforts of predicting the performance of the SPARC Tokamak fusion reactor, poised to be the first fusion device to study burning plasma conditions. And his papers on the topic are among the most read in nuclear fusion. Despite his young age, Pablo has authored over 30 peer-reviewed journal papers, a third of which is first author. Pablo has been the recipient of important awards during his academic career, including the Manson-Benedict Award and the Del Favero Doctoral Thesis Prize at MIT. And he was listed by the Forbes magazine as part of their 30 under 30 list in science in 2021. So Pablo, thank you very much for joining us today, at least virtually. And yeah, we're looking forward to your talk.
All right, thank you very much, Thomas. Let me share my screen. All right, can you see my screen?
Yes. Yes.
All right, perfect. Yeah, thank you very much for the introduction. As Thomas said, I'm Pablo Rodriguez-Fernandez. I'm a research scientist at the MIT Plasma Science and Fusion Center. I work on fusion energy, and in particular, about my work focuses on the core of tokamak plasmas. So as we are going to see in this talk, to create fusion, we need these very hot systems, these very hot plasmas. And my work is about predicting how hot the plasma can get, how much fusion we're going to get, fusion energy we're going to get out of it. And I study that computationally. So in this talk, what we're going to do is we're going to start with just basic concepts in fusion, a little bit of motivation, and what we do at MIT, how we think that we can make fusion a reality in the next years. So let's get started. So let's start with motivation. Why, excuse me?
Everything is fine. Everything is fine. Go ahead.
Okay. I heard. Yeah, sorry. Great. So let's start with a motivation. Why we're doing this. And the reason why we're doing this is because most energy generated worldwide still comes from burning fossil fuels. This is the world energy consumption by source, and even nowadays, more than 80% of our energy comes from burning oil, coal, and gas, and only a small portion comes from renewable energies. And this, of course, has a consequence in climate change, and we're going to suffer the consequences even more in the next years. And not only we need to reduce CO2 emissions to mitigate climate change at current power generation levels, but also the demand is growing. This is only in the US, it's only electricity generation. And even if we expect that our capacity of renewables, solar, wind, hydroelectric, all that will grow in the next years, and even assuming that our fission power plant capacity remains roughly constant, we are still going to be producing electricity from fossil fuels, more than 50%, or about 50% of that by 2050. If we want to meet the net zero goals by 2050, we need to develop a different energy solution, something that can substitute that baseload power generation and that can become part of the energy mix by 2050. And I put here a quotation mark, like a question mark, because this energy can be anything, but however, that new energy has to have a few features. It has to be environmentally friendly. It has to be abundant. We don't want to, have to figure out a different energy source in the next century. We want something that can stay with humanity from now on. I want something that is safe for humans and our environment, of course, that can be available for baseload power generation, that is like 24/7, and that we can control how much power a given station, a given power plant will produce. And we want something that is scalable, dispatchable, that fits into modern grids. We don't want to change the entire energy infrastructure of the world. And if we want to do that by 2050, in the US alone, that would require about 300 gigawatt of new installed power by 2050. And the question that I want to answer here, and the work that we do at my lab, is, can fusion be the game changer here? Can fusion be that energy, that baseload energy that substitutes natural gas and coal and oil? So let's learn a little bit about what fusion is. So here we have a very typical graph of the average binding energy per nucleon as a function of the mass number. And here we have the elements of the periodic table organized by mass number. And the only thing that you need to understand from this graph is that if you move upwards, if you move from the bottom to the top, that process would produce energy. Meaning if we start with heavy elements and we are able to split them together and we move towards like lower mass numbers, that produces energy. And that's actually what fission power plants do. They take uranium, plutonium, thorium, and they split them up into smaller pieces. And because you move towards the top, you produce energy. What we want to do in fusion is the opposite process. We want to take the lightest elements like hydrogen, helium, and when you put them together, you also move towards the upper part, because you're actually, when you fuse them, you end up with higher mass number elements. And that process also produces energy. Actually, in terms of energy density, fusion reactions are more energy dense than fission reactions. However, there is a problem, which is that those nuclei, those hydrogen nuclei are positively charged. And if you want to put them together close enough so that fusion happens, you need to actually fight the repulsive Coulomb force, the electrical force. And actually, when you try to put them so close together, that force is very, very big. So one may actually understand what's the probability of two nuclei fusing together instead of scattering, instead of repelling each other. And we can plot something that we call the rate coefficient, which is basically the probability of the fusion reaction as a function of the temperature, basically how fast those particles go. And here I'm plotting different reactions of two isotopes of hydrogen or with helium. And the most probable reaction is the reaction between deuterium and tritium, two isotopes of hydrogen. And if we want that reaction to be probable enough so that it happens with enough probability, we need to be in this area here. And if you translate that into temperature, we're talking about a temperature of the system of about 10 kiloelectron volt. Kiloelectron volt, when you translate that into a thermal energy in degrees that we can understand, it turns out that your system has to be at more than 100 million degrees for those reactions to happen with enough probability. That's about 10 times hotter than the center of our sun. It's very, very hot conditions to get fusion happen in the lab, in our devices, as we are going to see in a second. However, even though this sounds like science fiction, like having a system at 100 million degrees, it turns out that it's not that hard as it sounds. And the reason why that's the case is because this hydrogen gas, when you bring it up to 100 million degrees, is not a gas anymore. It's a plasma. Basically, you have charged particles like ions, nuclei, and electrons going around. And those charged particles, they are affected by magnetic fields. So if you're clever enough and you draw a magnetic field in such a way that these charged particles gyrate around the magnetic field, and you keep that away from any physical material, then you can keep something very hot without melting the walls of your machine. Actually, what we do is to close those magnetic field lines in circles, producing this donut shape, this ring shape that we call, well, this is a torus, basically. And the particles would go around this torus without touching the walls of the machine. And you can have something that's very, very hot using magnetic fields. That's the basic idea. And this is what we do in devices around the world. There are two main magnetic fusion devices, the Tokamak and the Accelerator. Both use very powerful electromagnets so that you create a magnetic field in the center of the machine, and you confine the plasma, this 100 million degrees gas, inside a vacuum chamber. There are some differences between the Tokamak and the Accelerator. However, historically, Tokamaks have been studied more, and Tokamaks are the, let's say, best performing devices right now. Accelerators, they have clear advantages, and they are progressing towards high performance, but still the Tokamak is our top device to do to contain this hot plasma. And that's the focus of my work, actually, and that's what I will be talking about today, about Tokamaks. So we have built many of these devices around the world. Actually, we have right now about 50 Tokamaks currently operating, and we have built about 170 of them. And we run experiments every day, and basically every year we attain new records. Actually, if you have been following up the news lately, our Asian colleagues have been getting amazing results with their.
Oh, Pablo, you switched off your microphone by accident.
Yeah, it said that the host muted me. I don't know what happened. Can you hear me now? Yeah. Now you are muted, but yes, I guess you are. Okay, sorry about that. I was saying that, yes, so we run these experiments every day and we get amazing results every year. However, we don't have fusion energy in our electrical grids right now. So how come that we have built and experimented with so many devices, but we still cannot produce electricity out of fusion? So to go from science experiments to energy or electricity generation devices, we must produce, of course, net energy. We have something in fusion called the fusion gain, or the engineering gain, which is basically the ratio of the power produced divided by the power required to run the device. Because of course, if you start with a hydrogen gas and you want to heat it up to such high temperatures, you consume energy. And to keep it at that temperature, you have to, the plasma needs to keep absorbing power. Otherwise, it will just flatten out and you will not get something hot. So that ratio being greater than 1 is what we want if we want to produce electricity, of course. But not only we haven't produced electricity ever, but we have never actually created a net power balance in the plasma. If you account for the power that is absorbed in the plasma and the power that is produced in the plasma, that ratio has never been greater than 1. Here we have a figure of devices over the years and how they have been getting closer and closer to our break-even curve, basically the Q = 1 curve. And after that, you start producing net energy. We made a lot of progress in the 1990s. And since then, we haven't been able to break those records. In fact, the record happened in 1997, where when the JET Tokamak in the UK created a plasma that transiently achieved a Q of 0.6. So it produced 60% of the energy that the plasma absorbed. It did that transiently, only for a few, let's say, a few hundred of milliseconds. They also reached lower Qs, lower fusion gains in a more steady way, but we have never actually reached higher performance than that. So how do we move forward and achieve fusion? Like, is this a showstopper since we haven't done it since the 90s? So what's going on? So let's learn a little bit about what matters for the performance of these tokamaks. So it turns out that tokamak plasma physics gives us a simple formula for the power generated by fusion reactions. We have that the power is proportional to this formula here, roughly. This is all, of course, very hand-wavy. But the basic idea is that these parameters at the beginning of the formula, if you want to run the machine in a safe and robust way, these first parameters have to be fixed. Otherwise, you're going to have plasmas that become unstable, or you explore regions of the parameter space that you have never explored before, things like that. So if we forget about these first parameters here, it turns out that the power depends on two things. Depends on the size of the machine, basically the radius of this tokamak, of this torus, and actually depends on basically the volume of the plasma, and the intensity of the magnetic field to the fourth power. So if you want to get energy, you want to get more fusion reactions, you either need bigger machines or machines with higher magnetic fields. Actually, if instead of doing these very hand-wavy, back-on-the-envelope calculations, you actually use codes and use more physics, you actually end up with very similar trends as before, where big machines and strong magnetic fields is what matters. In this plot here, you have size, the radius, and the magnetic field, and the fusion gain contours. So you basically want high fusion gain. You want to move towards this top right part of the figure. The record plasma that I mentioned earlier with the jet tokamak sits around here. It's about 3 meters machine with a little below 4 Tesla magnetic field. And it did not reach a break-even. It did not reach Q greater than 1. So this figure actually applies to that experiment. So to produce net energy, to move towards the high fusion gain contours, the fusion community already knew all these trends decades ago, and decided that in order to produce a net energy plasma, you needed to go to high size of the machine. And that's what the ITER device is. And the reason why the ITER device needed to be this big is because the magnetic field, the maximum magnetic field that you can produce at that size was actually limited by the engineering of superconductors. Basically, you need to build this electromagnet with superconducting materials, and the maximum magnetic field that you could reach with those superconductors was actually quite limited. So if you wanted, back then when ITER was designed, if you wanted to produce net energy, in fact, ITER has the goal of Q of 10. If you wanted to reach that, you needed to build machines that are big. Actually, ITER and
Sorry, Pablo, for interrupting you. I cannot hear you. The microphone is switched on, but I cannot hear you.
Oh.
Yes, now we're back. Now it's back.
Oh, okay. So should I repeat
yeah, the last 15 seconds or something like that.
Okay, I'm sorry about that. I don't know what happened. Yeah, so I was saying that decades ago, in order to reach a high fusion gain, in fact, ITER was designed with a Q of 10 fusion gain. Because of the limited technology of superconductors, ITER had to be designed with a very big size, basically with a very big measured radius of the torus. And ITER ended up having a measured radius of 6 meters. 6 meters, the measured radius of the plasma is very big. This is the machine, a schematic of the machine. This is a person here, so you can get an idea of the scale of how big ITER is. Here we have our plasma at 100 million degrees. And because it was so big, because it is so big, it is also very expensive and very complex to build. It actually required an international collaboration. Like about 30 nations are contributing funding and resources to build this machine. And it's being built in the south of France. It's right now at 80% construction. They started the construction in the early 2000s. And it will produce the first plasma in 2025. So it takes very long to build, and it ends up being very expensive. And how does the pathway to fusion looks like? So we start with our current machines, current devices. As I said, we have about 50 of these. We do experiments around the world. We study the plasma physics, but these are not producing net power plasmas. They're not producing burning plasmas. Instead, ITER will be a machine that will produce net power plasmas. As I said, it is suspected the first plasma in 2025. However, it will not produce net power until 2036. So it's a long time from construction or even from design in the 90s to fusion gain greater than 1. So that's kind of a little bit disappointing. Also because it's going to cost a lot of money. It's about more than $25 billion, and some estimates range it in between $40 and $50 billion in reality. And ITER will not produce electricity. It's an experiment. We're going to study the physics of these burning plasmas. The next step, that we call demo, that's an energy producing machine. That's an electricity producing machine. It's a prototype. And there are several designs under consideration, and it's likely going to be larger and more expensive than ITER. And as I said at the beginning of my presentation, to make an impact by 2050, we said that the US alone needed about 300 gigawatts of power. And that means we need 300 of these guys here, fully operating at 1 gigawatt electric each, to really make an impact. So one should ask the question of, is fusion simply too expensive, slow to ever be economically attractive? That's the question that we ask ourselves at MIT and at my lab. So let's go back and take a look at this graph that I showed earlier about how to get high performance plasmas. So we said that ITER was designed at a very big size because it was limited by the magnetic fields. And ideally, it would be fantastic if we could actually operate down here in a region in which you also have high gain, high performance, but you can have the devices at low size. And actually, that's what it's been, we are proving that that's going to be possible thanks to a new type of superconductor. The high temperature superconductors, which appeared commercially in the last, I would say, 1 decade or so, these materials allow, in principle, operation at high magnetic fields, so that instead of having machines with large size, you can have machines with a very high magnetic field. In this plot here, you see the window of operation of the low temperature superconductors, those that are used for a machine like ITER, in which the magnetic field is quite limited for operating in the superconducting state. These high temperature superconductors, these new materials actually have much larger window of operation. And that really can be a game changer for fusion energy. In fact, MIT has developed, in collaboration with the private company Commonwealth Fusion Systems, which spun off from MIT a few years ago in 2018. And we are developing large bore magnets with this superconducting material. We are building cables, and we are building these electromagnets, these magnetic field coils. In fact, last September, we broke the record of high magnetic field at this size. We reached 20 Tesla in a large bore magnet, and this was in the New York Times. It was all over the news, and actually after that, the company has received about $2 billion of funding to use these magnets to build our own ITER, and that's what I'm gonna show you here. So this is ITER, right? I said that it's a big machine. Here we have a person, very expensive, and it will produce 10 times more energy in the plasma than it will absorb, right? Thanks to these magnets, the same performance can be achieved in a much smaller machine. And that's what we are working on with the SPARC Tokamak. You see here at scale. a much smaller volume, much smaller cost, much faster to build, basically the same performance. And that's enabled by these new high temperature superconductors. We actually entered in construction, we started construction of this machine in 2021, and we are expecting to finish it and to turn it on in 2025. And so basically 3 years from now, it's quite exciting. And we're going to produce net power, net energy plasmas soon after we turn it on. I like to show this picture here. This is me in the construction site in April 2021. There was nothing there. And a few months later, we already see the facility being built. And this is quite exciting because this is very fast progress. In a few months, you already can see the place where the Tokamak will be. And construction is going on schedule. And in 3 years, we're going to be producing net energy plasmas. So what is this device? What is SPARC? So SPARC is saying net energy, compact, high magnetic field, deuterium and tritium fusing device. And actually, we presented the concept of this machine to the fusion community in 2018 in one of the main conferences in the US. And the latest version has been, or the machine, the version 2, has been thoroughly studied and peer-reviewed in the Journal of Plasma Physics. It's all in open access with 7 papers and a big collaboration among many institutions and many people. This is the schematic of the machine. And when we presented that, it was also all over the news. It was even mentioned in a late night show, which was quite fun. So one of the things is that the design of this SPARC Tokamak is largely based on the design of ITER and other conventional tokamaks. What we are doing is take the knowledge of building tokamaks that we have been, as I said, building them since the 60s. We have built many of them, so we know how to. We have been operating with tungsten walls, with heated by ion cyclotron range of frequency waves. And we have also built high field tokamaks. And the thing is that the reason why SPARC is so interesting is because the compact size means that we can actually build it smaller than devices that exist nowadays. But because of the magnetic field, we can produce net energy. This is to scale the cross-section of SPARC compared to devices that are operating right now. So SPARC is smaller than the JET tokamak that produced 60%, remember the fusion gain of 0.6 back in the 90s. So this is very exciting to be able to build a machine small that produces net power. And these are the parameters. These kind of like the typical set of plasma parameters that describe a given tokamak. And we're gonna go one by one to see what these parameters mean. The first one is the major radius. So instead of the 6 meters of ITER, we have 1.85 meters of major radius in the SPARC. And this is what we call in fusion a medium-sized device. And that means that it's cheaper and faster to build instead of having to build them at a very big size. This is the minor radius of the torus. And what this means is that the aspect ratio of A over R is standard. So we expect no surprise in terms of the plasma physics of the core of these devices. This is where all the, let's say, the magic of SPARC comes, the magnetic field, this 12.2 Tesla in the center of the plasma. And that's unprecedented magnetic field at this size. That's what is giving us the high performance. We can operate these plasmas at a high electrical current. So these tokamaks require that you make a current go through the plasma. And the reason why you need that is because the magnetic field has to have a helical shape so that the particles are confined, all right? And the plasma current, the electrical current that we're gonna be driving in SPARC is 8.7 megaamperes. And that's the same normalized current, something that we call the Q safety factor as ITER. So we expect no extra risk. It's all very standard. This is the normalized density, which is smaller than ITER, and that means that this has less risk than ITER. this is the power that we're going to put in the plasma. We do that with electromagnetic waves. So we launch waves at a given frequency that so that they resonate with some motion in the plasma, the cyclotron motion of the ions, and that those waves are absorbed, and we're going to introduce 11 megawatts of power, and that's a reasonable amount of input power. We know how to do that. We have had machines where we have introduced much more. And these last ones are the shaping parameters. So basically here you've seen the cross section that the plasma is not really circular. It has this weird like triangular shape, if you wish. So that's given by these two parameters, elongation and triangularity. And again, this is standard geometry, so we expect no surprises. So basically with this slide here, what I want to convey is that all the relevant plasma parameters are quite standard. We expect no new physics to appear in these new burning plasma regimes. The only thing that has been different is the absolute value of the magnetic field, which is what is going to give us this extra performance, as we saw earlier. So, all right, so this is all like very hand wavy, let's say, right? It's like some very basic rules. So, but how do we make sure that plasmas will really produce net energy? So we need to do better than just back on the envelope calculations. So we have taken a 3 steps approach to predict the performance of SPARC. One of them is using global empirical models. Basically take a big database of experiments that we have had all over the years and obtain how well the energy is confined in the plasma as a function of the engineering parameters of the machine. And you end up with scaling laws, like these 1 power laws, with those coefficients being obtained by regression against the database. And this tells you basically the performance of your machine, like how well is the energy in the plasma being kept there, being confined. And we do that. We create maps of performance like this one here, as a function of the density of the plasma, so how many particles we are confining, and as a function of the temperature, so how hot the plasma gets. And this yellow region here is the operational window. Basically, a window where we produce net energy and where we are actually below the limits of the machine. So for example, this black line here indicates 25. This is the total input power that we put in the plasma. So we have to be below 25 megawatts because that's how much power we're actually installing in the plasma. And it turns out that the optimum performance, the optimum fusion gain ends up here, this magenta purple dot, and that's a Q of 11. So in this, using these global empirical models, we predict that SPARC can produce 11 times more energy than that we introduce. Remember that ITER was designed to be a Q of 10, so this is even higher performance than ITER, thanks to the magnetic field and the plasma current being very high. And actually, something very interesting is that, yes, we get a Q of around 11 when we operate at the nominal performance. But even if we run SPARC, we run experiments, and suddenly something bad happens, I don't know, like some instability that we did not expect or something else, even with the graded performance of like 30 or 40% lower performance than we expect, even in that case, we are still producing net energy. So it's a very robust operational point, and that has been the philosophy of the design of this machine at MIT and CFS, the company. However, this is all with empirical models, right? Global empirical based models. So all based on data, not much physics. So another approach that we took is to use physics models, so simulations, and simulations of the behavior of the plasma, of the plasma dynamics are simulations that are very expensive. So one thing that we do, computationally expensive. So one thing that we do in plasma physics is to make some assumptions to the physics that we expect. In particular, we make assumptions of how the turbulence looks like, and we use reduced models that can be run fast. When we use this technique, we can predict where in the plasma we are depositing our power. So this is the cross-section of the plasma here. We're only looking at one slice, let's say. Here is our antenna in green on the right, and this is where the power of these electromagnetic waves are being absorbed. And you want them to be absorbed in the middle of the plasma so that, you know, the energy gets better confined there. And you can predict using these reduced physics models what is the temperature that the plasma will have. So this is in normalized radius. So from the center, 0, to the edge of the plasma, which is 1, this is the temperature. So we end up with 20 keV, kiloelectron volts in the center, which is about 200 million degrees, with an average temperature of in the order of 10. And this is the density as well. So we use these simulations to predict that, what we call the temperature and density profiles. And the way we do it is that in order to run these simulations in a reasonable computational time, we use assumptions of how you simulate turbulence. And the way we do it is to assume that turbulence is quasi-linear, meaning that at every radial location and every location in the plasma, you can determine what kind of waves are unstable linearly. And then you have rules that tells you what is the energy flux that is expected from turbulence based on those linear features of those linear solutions. And the reason why you do this is because then you don't need to run expensive nonlinear simulations to get a result. So you basically obtain what is the growth rate of your instabilities as a function of wave number, and obtain an expression for your heat flux. And if you have a heat flux code, heat flux simulation, and you have how much power you put in, you can determine what's the gradient that the plasma will attain. And that will tell you how hot the plasma gets in the center. And when we do this, we obtain that the fusion gain of SPARC is a fusion gain of 9, which is very close to the empirical prediction. So we have two very different workflows that basically give you the same result, which was quite fascinating. And finally, we said, okay, we have these reduced physics models, but the physics regime that SPARC will operate at, we have never explored it because we have never had a burning plasma. So we said, okay, first principle simulations of turbulence are expensive, but let's do it for SPARC. Let's try to figure out a way to run these simulations in a cheaper way to obtain what is the prediction of performance from first principles. So basically from the dynamics, from Maxwell's so basically a kinetic equation plus Maxwell's equations, what is the temperature that this thermal plasma reaches, right? So this is just a video of how typical turbulence simulation in a Tokamak. So we have eddy structures that transport energy and particles from the inside to the outside. So basically against the gradient, as you expect in a diffusive-like transport behavior. So these simulations are very expensive. However, we developed a machine learning-based technique, a surrogate optimization technique, to run these simulations about a factor of 5 cheaper. And thanks to these new techniques, we could predict the temperature and density of the plasma from first principles for SPARC, becoming that simulation became the highest fidelity prediction ever done of a machine, of a fusion device, and was published in the MIT News. And this makes SPARC the best predicted machine in the world, even if it has been around for only a few years. So this was quite exciting. This happened actually less than I think a month ago or something like that. And in summary here is that we have that the global models predict 11 times more energy than you put in. Reduced physics models predict about 9. And the first principle simulation, so the most accurate you can do, predict a Q of 8. And even though there's some discrepancy, this level of agreement between these very different independent workflows is astonishing. Like in plasma physics, we have high uncertainties typically. So the fact that all transport models indicate that SPARC will create plasma with a fusion gain between 8 and 11 gives a lot of confidence that we can actually surpass the mission, which is producing a fusion gain greater than 2. So every model indicates that that's going to be the case. And we're going to be studying this kind of plasmas in 2025, validating the models to understand how well these, for example, reduced physics models or how the empirical models, how well they predict performance of these Barton plasmas. And if you remember before that I said that we're going to move from current devices to ITER and then from ITER to demo, we have a very similar approach in our path. And we start with the knowledge that has been gathered in the community for many years. We're going to build SPARC. We're building SPARC that will be ready by 2025. And we plan that from SPARC to electricity producing prototype power plant, which we call ARC. That would happen in early 2030s, 2035 at most. That's the plan of MIT and the company. And SPARC will not produce electricity. It's similar to ITER in that regard, but ARC will. And once we demonstrate electricity production in ARC, we can start commercializing and hopefully by 2050 make an impact and have many of these machines all around the world. And the reason why we need to build SPARC first and not go directly to ARC. So this is a schematic of how a fusion power plant looks like. So we have our Tokamak with our plasma in the center producing heat, producing energy by fusion reactions. And this heat is absorbed by some kind of cooling liquid, cooling fluid, and that is used to move a turbine. And that turbine generates electricity in a very similar way as any power plant in the world works right now. So, but instead of having a huge oven burning coal, you have a hot plasma producing the energy. And the reason why we need to build SPARC is because we want first to have a test bed to run experiments and understand how to best design and build ARC, the power plant. Because we must not forget that the final goal is to put electricity into the grid, even if those experiments are super cool and fascinating and awesome. We need to put electricity in the grid if we want fusion to have a future as an energy source. And the thing is that from existing experiments, in whatever metric you want, in plasma physics variables or performance metrics, are, let's say, around here. This is all, of course, this is a cartoon picture. And our power plant ARC is around here. And since it's an extrapolation in many of the parameters, the error bar, let's say the uncertainties on how to build ARC are big. And our goal is that with SPARC, we can actually fill that gap, bridge from existing experiments to fusion relevant plasmas, or like reactor relevant plasmas, so that we can actually reduce the uncertainty in the design of the power plant. And even if our empirical and physics-based models and these first principle simulations that I showed earlier all indicate and all give confidence that ARC and SPARC and ARC design points are feasible, still we have large uncertainties. And that's why we need to build SPARC first in a few years, and after that move and build the next step, which is ARC. So this is actually the end of my presentation. I purposely left a few minutes for questions. So thank you very much all for your attention. I leave here a few references. I'm gonna share later this slide deck with you guys if you're interested in following some links for the papers. And what we're trying to do here is to make fusion be the energy that can substitute the fossil fuels that are used nowadays. And I hope that you got the impression that that can be done, and we're gonna be exploring those devices soon. So thank you very much, and I'm open to questions.
Yeah, thank you, Pablo, for this wonderful, very interesting talk, very interesting work. Yeah, are there comments, questions from the audience? Yeah, there is one question from Gloria Königsberger. Gloria, go ahead.
Hi, Pablo. Thank you very much for the fascinating talk.
Thank you.
I have a whole bunch of questions. I'm an astrophysicist.
Okay.
So I understand nuclear reaction rates, but at the center of the sun.
Yes.
And so I was wondering, I have several questions here. The first one is, how do you inject the plasma into the magnetic field bottle? Is this done with a certain velocity distribution, or is it there and then you heat it? How does this happen?
Yeah, so that's a great question. So the way we do it is we start with we have a vacuum chamber. We have a very good vacuum, and then we have valves that would inject small amount of this hydrogen gas, deuterium and tritium. And we have a system that basically breaks down. So that what we want to do is to start having a plasma, right? So we have a electrical arc or some kind of other system to break down the plasma, and then we turn on the magnetic fields and the electrical current, the induced electrical current, so that we make that plasma grow from something that is very small, just a small region being break down, to something that is big, and we start heating it up with electromagnetic waves. So we start with something that is, let's say, at very low temperature, low density, and you want to create a first plasma that then you grow and make it hot.
By grow, do you mean that you inject energy into the plasma?
Yes, so
by keeping the density constant.
Well, at the beginning of the plasma discharge, we keep putting gas so that the density grows to the level that we want the plasma to operate at. But then while that happens, we're actually inducing an electrical current. So what we do in Tokamak is we have this solenoid in the center. So we have kind of like a transformer action. So we induce this current in the toroidal direction, and the particle will create that current basically. And with resistance heating, so with Joule heating, you start already giving energy to the plasma. Because the plasma will have some resistance, and you can start heating the plasma just by collisions, by collisional heating. And then you want to make it hotter is when you start like launching waves that resonate with the motion of those particles. So so at the same time, when you start in the plasma, you start putting particles and you start putting heat until it gets to the level that you want.
Okay, and then so the other question is, what is your limitation on the density? So you seem to be having relatively low density plasmas. Is it stability, or where is the limitation?
Yes, it's actually stability. So it's MHD, magnetohydrodynamics stability. So there is a empirical limit in tokamaks, although right now in the last years there have been theoretical explanations for it, but there is a maximum density that you can operate safely the plasma, otherwise it would disrupt. So there is a kind of like a kink instability or something in the plasma that happens and you start losing confinement. So there is a maximum density that is called the Greenwald density limit that you operate the plasma at. And actually that's a very interesting question, because that's one of the reasons why SPARC has such high performance, is because that maximum density that you can operate the plasma safely depends on the magnetic field. So if you have a higher magnetic field machines, then you can actually have higher densities. And higher density means more power, because you then have more particles that are able to fuse together. So that's one of the advantages of the high magnetic field. Is to be able to operate at high density. It also lets you operate at high currents, which is also another limit. So there is these two limits on electrical current and density. Those two things, the higher they are, the best for fusion. And those two things get better with magnetic fields. So that's the reason. Yeah.
Great. Thank you so much.
Thank you.
Okay. Are there further comments, questions? Yeah, there is one from Luis Mochan. Luis, go ahead.
Can you talk us a little bit more about these electromagnetic waves? What kind of frequencies, what kind of powers?
Yeah, no, that's a good question. So the frequency of the waves depends on the magnetic field that you operate. So basically, your ions in the plasma will be gyrating around magnetic field lines in the center with a given frequency that depends on the magnetic field strength. So because the SPARC, we are operating with 12 Tesla in the center. If we want the waves to resonate in the center, we actually are launching them at 120 megahertz. So we launch waves at 120 megahertz that they are absorbed roughly in the center. And we are installing about 25 megawatts of those 120 megahertz waves. However, that doesn't mean that the more waves you launch, the higher performance you get. Actually, it turns out that the models indicate that if you launch about 10 megawatts, that's actually the optimum point for performance.
Okay, thanks.
Thanks.
Okay, are there further comments, questions from the audience? Yeah, there's some question from Jaime Roquico. Jaime, go ahead. You can switch on your microphone, Jaime. And
thank you very much, Dr. Rodriguez, for your talk.
Thanks.
My question is, on your simulations, did you take into account the plasma wall interaction? Your Tokamak is pretty small, but your density and energy is as compatible as that with ITER or JET. So I would expect your Tokamak would be somewhat attacked by particles that would sputter impurities. Did you take that into your simulations into account?
That's a great question. Yes, we do take into account the impurities. We do not have models of like physics-based understanding of how many impurities the plasma will have. So the approach that we did is to assume a level of impurities similar to what ITER assumed and similar to what current devices can achieve in terms of like tungsten, because actually our walls are made of tungsten. So we assume that tungsten concentration in the plasma, which actually radiates a lot of power. So it's very important to assume that you have some tungsten in the plasma. And in terms of the heat flux to the walls, so the way it happens, I don't know how familiar you are with this, but in Tokamaks, the way we do it is that we have this confined plasma region, and then the plasma has what we call a scrape-off layer. So the edge of the plasma, actually, the particles go, have a parallel motion to the magnetic field and end up in a region that we call the diverter. Okay, so the diverter is where these plasma surface interactions occur. And we are taking into account that there's an entire overview paper on how we are going to handle those heat fluxes, very high heat fluxes. And in summary, one of the techniques that we're going to use is that we have placed magnetic field coils very close to the plasma in the diverter region so that we can actually move the leg of the plasma, so that we can spread the heat flux in a larger diverter region so that it's not only concentrating one spot. So we are doing simulations with multi-physics simulations to understand how fast you have to do that motion. So we are taking into account all that. However, something very important that actually brings me, your question is I want to indicate that SPARC, we're going to run experiments in SPARC for a short period of time. We're going to run them for about 10 seconds, which is enough to study the physics that we need. A future power plant, which needs to run for much longer, I mean, you could have it in a sustained manner, or you could have it in pulses, but pulses that last minutes at least, or hours. And for a power plant, we still need to find solutions to how we're going to handle the diverter heat fluxes. And actually, SPARC is one of the machines where we are going to explore those options. So as I said earlier, actually, let me bring this slide here. So one of the like extrapolations in the parameter space from current experiments to ARC is especially how we're going to handle those heat fluxes. And in SPARC, we're going to explore options and alternatives. And that's something that will hopefully bring us close to a power plant design.
Okay, thank you.
Thanks.
Okay, Gloria, you have another question?
Yes, I was going to ask something along the lines of the duration over which you can sustain the fusion, because I mean, you can sustain fusion as long as you have hydrogen and then you have helium. So you have to have a mechanism by which you're feeding more hydrogen and taking out the helium so that this can be something that's running permanently. Or I don't know what's being visualized in this respect.
Yes, so that's a great question. Yes, so in principle, the idea is that we are going to be, like, of course, the hydrogen nuclei that are part of the plasma will be fusing and will be disappearing. So you have to keep introducing particles in the plasma. And then you have this helium that is produced that is also kept in the plasma in the form of what we call thermal helium ash. And that's something that we have to remove also in the divertor region. So there is something that we call the particle confinement time. So that basically tells you how well will the helium be confined. You want the helium not to be confined. You want the helium to leave quickly. And that's one of the parameters that we do not have good physics understanding on how to predict it. So that's one of the focuses of SPARC, running experiments to understand how that looks like for a power plant and how we can find solutions to it.
Thank you.
Thanks.
Okay, Luis, you have another question?
Yes, I don't remember if you mentioned it, but what would be the cost of SPARC, the cost of ARC, and the cost of generating energy, assuming that everything goes well?
Yes, no, that's a great question. So SPARC, it's going to be in the order of or less than $1 billion. Around that's going to be roughly the cost. So that's about a factor of 40 cheaper than ITER, which is already a great savings, let's say. The cost of ARC has not been determined yet. There is many things still to decide in terms of what's the operational regime, like what's going to be the optimum size, what's going to be the optimum magnetic field. We actually hope that, so this company, Commonwealth Fusion Systems, is the one who is developing the magnets with these superconductors, and that is determining what is the cheapest way to put electricity to the grid. I don't think they have estimates yet on how expensive ARC will be. The thing is that this is different from what we are used to energy generation, right? Because the cost of energy comes from the cost of your fuel. But in the case of fusion, all the cost comes from the capital cost of building the machine. Then the fuel is virtually like unlimited and virtually free, let's say, compared to the capital cost. So it's a complete change of paradigm. And we are still looking at what's the optimum way of dealing with that. Also, what's the optimum way? Like, should we have 1 gigawatt electric power plant? So should we have smaller ones, like 200 megawatts, to be able to deploy in a faster time scale? So those are things that we're still, that it still needs to be decided.
Okay, thank you.
Okay, are there further questions, comments? I actually have one question. You mentioned now the fuel of the fusion reactor, but you need tritium, right?
That's so
from where do you get it?
That's a great question. Yes, so it turns out that in a power plant, so actually it's good that I have this figure here. The result of the fusion reaction, so you have these deuterium and tritium nuclei, they fuse together, they produce a helium and they produce a neutron, right? This neutron is not confined because it doesn't have a charge, so it will just leave the plasma. And the idea is that we're going to have a blanket, we call it blanket in fusion, which is a layer of either liquid or solid lithium. And that neutron will react with this lithium and will produce a tritium as a result. And the idea is that in a power plant, we're going to take the tritium that is produced by that lithium plus neutron reaction, and we're going to put it back into the chamber. So basically, the idea is that in a power plant in the future, we are not going to have tritium going in or out. It will produce its own tritium. The overall balance will be, we need deuterium and we need lithium. Those are the two things. Deuterium can be obtained easily from seawater. Actually, 1 out of 6,000 atoms is deuterium in the hydrogen in seawater. And then the lithium comes from the earth crust. It's a limited resource, of course, but the density, the energy density of this reaction is so high that you actually don't need much lithium to power to get the power plant going. So to start the process, we need tritium. And actually SPARC and ITER will need tritium to operate. And to start a machine, we do need tritium. Then it will start producing its own tritium. But you have to have something to start with. And there's a whole industry that is about producing this tritium. Usually you produce it from fission power plants. Actually, there's a Canadian type, the CANDU reactors that produce tritium. So yes, the idea is that you only need tritium to start operation. After that, you should be producing your own tritium.
I see. This lithium shielding, is it planned for SPARC or only for ARC?
Only for ARC.
That's only for ARC.
So in parallel to SPARC, MIT and CFS, the company, they are building smaller experiments where we're going to explore this tritium production. So we're going to have a deposit, let's say, of lithium, and we're going to have a neutron source, and we're going to be studying the dynamics and the behavior of these tritium breeding experiments, but SPARC will not have lithium in itself.
Okay, I see. Did I understand correctly that in some way you benefit from ITER, as you said you took essentially the same device now on a smaller scale with this superconducting magnets? Is it correct, or?
So sorry, you were a little bit cut out, so I don't know if I understood correctly. So your question is whether we are taking a smaller version of ITER?
Yeah, as far as my question is, did you benefit from the design and the research, more the engineering of ITER?
Oh, totally. Yes, we have been able to move this fast. So from start of the design of SPARC in 2017, roughly, to building it and finishing in 2025. The reason why we can do that so fast because there has been so much research and scientific output and engineering of ITER. So we owe to ITER all that. All the plasma physics that ITER, the community, international community has been studied for ITER is completely applicable to SPARC. Of course, there's some difference in the parameter space, but usually in dimensionless parameters, it's very, very similar to ITER. So dimensionless is very similar, but the difference is that the high magnetic field in absolute units gives you this higher fusion power, because basically plasma physics is a domain that depends mostly on dimensionless parameters, but nuclear physics depends mostly on absolute parameters. So fusion is a nuclear process. So that's why sorry, I'm going too far, but yes, I hope I answered your question.
Yeah. Okay. What do you think? Would it be a strategy at some point or would it be possible to upgrade ITER with this high temperature superconductors?
No. No, that cannot happen. The construction of ITER started a long time ago. They're now actually assembling these very big magnets, and ITER will not be able to upgrade to take into consideration this. However, the research that will be done in ITER will still be useful to power plants. I'm not saying that ITER won't be useful, but it will not take advantage of this new technology. However, if, let me go back. Yeah, so the designs of demo, that's something that could take into consideration the high temperature superconductor magnets. So the international community at different countries, different labs could still develop a demo version with high temperature superconductors. Of course, we're doing that at MIT and CFS, but there could also be other designs that take into consideration that. In fact, there is also, so all that I've explained today is tokamaks, right? There's all their devices like accelerators, and actually something that we call the spherical tokamak, which is it has different engineering. And those two there are groups around the world and actually companies that are exploiting high temperature superconductors for those designs as well. So there's something quite clear, which is that the future of fusion looks high temperature superconducting. Whatever the design ends up being of the most optimum device, that's what remains to be seen.
Okay. Yeah, there's another question from Luis Mocha.
It's just curiosity. Is there a simple way to understand the reason for the fourth power, B to the fourth, the magnetic field to the fourth power in the power you generate?
Yeah, that's a great question. The reason is that, let me think. Yeah, so, I'm trying to think of how that formula is derived to give you a better idea. But that formula is actually derived using the limits that actually I mentioned earlier. Like there is a maximum density and a maximum electrical current that you can run the plasma. And those two things mean more energy, all right? And it turns out that the empirical limits, so the formulas that determine what is the maximum value of those two things, depend on the magnetic field. So when you take those into account and you plug that into the fusion power formula, you end up with the fourth power. Because it turns out that another simple way of seeing that formula is the fusion power is proportional to the square of the pressure. Mm-hmm. So the pressure of the plasma is going to be a function of the temperature and the density, NT, let's say. And that pressure square, because the limits on how hot and how dense you can have the plasma, that depends on the magnetic field square itself. Okay. So square, fourth power. Yeah, sorry, okay. Yeah.
Thanks.
Yeah, so because actually something interesting, actually, let me go back. So in this formula here, this is the energy confinement time that determines basically the performance, so how well you can confine the energy. If you see the magnetic field, it's only raised to the 0.15, so that's very low. But the reason why magnetic field is good is because the current and the density, those two things are raised to a higher power, and you can run the plasma with higher values of those two things thanks to the magnetic field itself. Yeah, and that's because the plasma is so the magnetic field is in a helical shape, right? You have a toroidal component and a poloidal component. And if you have a low magnetic field, so the toroidal component is very low, if you run it with high poloidal component, that becomes very unstable and you start having some instabilities. If you have then a larger magnetic field that is confining the entire thing, it's more constricted and more stable. And that's what gives you the possibility to run with higher currents and densities. Yeah.
Okay. Yeah. Thank you very much. Are there further comments, questions from the audience? Yeah. If this is not the case, Pablo, I think from 2025, you said SPARC is planned to operate as well as ITER, right?
Yes. Both are scheduled to start in 2025. However, ITER will take more than 10 years to introduce tritium to produce power. However, SPARC, we want to do it in a matter of months. So we want to do it at the end of 2025 or maybe 2026. So okay. We're not going to wait that much. But yeah, I hope you guys remember this talk that I gave. And
okay.
Let's see.
Let's see. Yeah. Keep our fingers crossed. This is that it will work. And yeah, thank you very much, Pablo, for this wonderful talk. Thank you for joining us today, at least virtually. And I hope to see you the next time in person.
Thank you very much. I enjoyed the talk a lot, and the questions were great. So.